All right, in 15.5, we're going to continue talking about simplifying. So the I can statement today is I can simplify and perform operations with square roots. So we used exponents last couple of times. Now we're going to be talking about square roots and radicals and stuff like that. So here's the warm-up. It says in the problem 3 to the second, 3 squared, that turns it into 3 times 3, and that equals 9. So we all know that. What squaring does is it changes one factor into a pair of factors. So if we take a look at the kind of the opposite type of problem, if we take the square root of 9, we could write 9 as 3 times 3, and we've got this pair of factors underneath, and it turns into 1 on the outside. So a square root changes a pair of factors into one factor. So they kind of do the opposite. Here when we're squaring, we take one of these 3's, turn it into 2. Here when we're taking the square root, we take 2 of these and we turn it into 1. All right, so that idea works really well when we're simplifying things. So what we've got here is we've got a pair of 5's. So if we've got a pair of 5's, we take that on the outside, and the answer on this one is 5, or you can just know that 5 squared is 25. On this one, when we have to simplify something that's not a perfect square, it's a little bit more complicated, but we can still use the same idea. So this would be 2 times 2 times 3, because 4 times 3 is 12. We've got a pair of 2's here. So we've got a 2 here, and then we've got the 3 left on the inside. So there's our answer. Same type of thing on this one. This would be 3 times 6. And 6 is 3 times 2, so we've got a pair of 3's there. So this is going to be 3 radical 2. And then 125, hopefully you've got that one memorized. That's actually 5 cubed, so it's 3 5's. Pair of 5's there, so we're going to have a 5 on the outside and a 5 stuck on the inside. And go ahead and circle that. Now, there are lots of skills in math that involve learning how to do something, and then we actually learn how to undo it. We learn how to reverse whatever that process was. And when two operations undo each other, I'm hoping that you know what this is because we've probably mentioned this about a million times, we call them inverse operations. So inverse operations, that means they undo each other. And taking the square root is the inverse of squaring. Taking the square root is the inverse of squaring, okay? Now, simplifying a square root works the same way whether the factors are numbers or whether they're variables. We're still looking for pairs of factors, okay? So we take out pairs of factors, and any factor that doesn't have a pair gets left or stuck underneath the radical. So let's go ahead and take a look at this. And then for the purpose of this explanation, we're going to assume that all the variables represent positive numbers. So on this one, we've got the square root of 12x. So I'm going to do the same thing that I did before. So this is going to be 2 times 2 times 3 times x. I just factor that, and I look for pairs of factors. Here's a pair of 2's. So we've got a 2 on the outside, but notice that the 3 and the x don't have any pairs, so what's stuck underneath is a 3x, and that's the answer. It's literally that simple, even when we're working with variables. So on this next one, let's take a look. We had a 3 times a 3 times a 2 before for the 18, and then this would be y times y. Now, if you want to go ahead and write it out as y times y, that's okay. If you want to look at this and just say, hey, there's 2 y's, that's going to be a pair. That's totally fine. So a pair of y's, a pair of 3's. So we have a 3 and a y on the outside, the 2 stuck underneath, and there's the answer on that one. Take a look at this one here. We've got a 5 times a 5 times a 5, and then we've got z, z, and z. So pair of 5's, pair of z's. So we're going to have a 5z on the outside, and look at what's stuck underneath. We've got a 5 there, and we've got a z from that one, so we'll go ahead and circle there. Now, I'm hoping 32 rings a bell. That's one of those ugly numbers that we deal with all the time. It's actually, whoops, take that back. I'm thinking backwards here. It's actually 5 2's, okay? So there's already a 5 out front. What we're looking for is pairs. There's a pair of 2's. There's a pair of 2's. So we're going to have 2 2's on the outside. So if I wanted to write them down, I totally could. There's that 2 stuck underneath. But it would probably be easier if I just said, hey, 2 2's on the outside. Again, it's all multiplication. That would make a 4. 5 times 4 would be 20. So we get 20 radical 2. So we'll go ahead and circle that one. Now, this one's a little bit more complicated because, look, we've got more than one variable and we've got some larger exponents. So here's the way I want you to think about these. We've already got a -3 on the outside. We've got a 2 and a 3 there for the 6. So we don't have any pairs there. But we've got 4 x's. Well, if you've got 4 x's, how many pairs is that? It's 2 pairs. So if you have to write it out like this, that's totally okay. What would be awesome is if you can look at that and say, oh, that's just 2 pairs, so I'm going to write x squared out on the outside. Okay. What's going to be stuck underneath is that 6, and then let's see if we can think our way through this one. If I've got 7 y's underneath the radical, how many pairs do we have if we have 7 y's? Well, if they come in pairs, that would be 6 of them would make 3 pairs. So if you've got 7 y's, you've got 3 pairs. So I'm going to write y cubed on the outside, and then 1 of those would be left. We basically took 6 of them out. That means 3 on the outside. Okay, 3 pairs, and then we're left with a y underneath. So this right here would be the answer. Okay, so let's come down here and let's take a look at what we've got next. Now, there are lots of times where we need to simplify radical expressions that have more than one term. And when we're dealing with variable expressions, again, we talked about this, like terms have the same variables and the same exponents. Or we actually changed that up and we said they have the same base and the same exponent to be a little bit more inclusive, and that will help out in the long run. Okay, but when we're dealing with radicals, like terms have the same root. Okay, so what that means is they have the same index. That means they're square roots, they're cube roots, they're fourth roots, or whatever. So they've got to have the same index, and they've got to have the same word here is radicand. The radicand means what's underneath the radical. So we want to have the same root and the same radicand. Now, most of the problems that we're going to do, they're all square roots, so they are going to have the same root. We just want to make sure that they have the same radicand. And what we're going to do most of the time, almost always, we want to simplify each term. So let's write simplify here. So we want to simplify the radical before we determine whether or not they can be combined. And you'll see what I mean in just a second. So if we take a look at this one right here, neither one of these can be simplified. They have the same root, they have the same radicand. If I have one of these plus another one of these, I automatically get 2 of those. And that right there is the answer. It's as simple as that. Now, when we look at something like this, at the square root of 48 plus the square root of 48, clearly those have the same root and they have the same radicand, so I'd end up with 2 radical 48. But if you're tempted to stop right there, please don't, because this isn't simplified. We always want to simplify this as much as we can. So what we're going to do on this one is we're going to say, look, this is going to be 2 times, and the square root of 48 is, let's write it this way. Let's say the 16 times 3. Because this is a pair of 4s. Now, you could break this down all the way into a bunch of 2s and a 3 and stuff like that, but it's just easier. The minute you see a pair of factors, let's go ahead and pull that on the outside. So we end up with a 4 and a 2 on the outside, so that's going to be 8, and we end up with 8 radical 3. Now, this is one way to do it. Another way to do it would be to simplify each one of these separately. And I'll give you this. It would be a little bit silly to do that on this one. So this is going to be 4 times 4 times 3. So this is going to be 4 radical 3. And the other one is a repeat of that. So that's going to be 4 radical 3. So if I have 4 radical 3 plus 4 radical 3, I get 8 radical 3. It's the same answer either way. So what I want to really look at are things like this, where we look at this and we say, wait a minute, they both have the same root, they're both square roots, but this has a radicand of 7 and this has a radicand of 28. No way we're going to be able to combine those. We can if we simplify them. So 4 radical 7 doesn't have any factors other than 1 and 7, so there are no pairs there. But on 28, this would be 2 times 2 times 7. So we're going to end up with negative 18, and then the 7 is stuck underneath. So I have 4 radical 7 minus 18 radical 7. If I've got 4 of these minus 18 of these, I've got minus 14 of those. So there's the answer on that one. That one has like terms. We can go ahead and combine those. So let's take a look at this. Again, it doesn't look like they can be combined, but let's check. Let's simplify this. Again, this was 3 times 3 times 2, so we've got 3 radical 2 plus 4 radical 2, and lo and behold, they are like terms. Same root and same radicand, so this is going to be 7 radical 2. We'll circle that. And then this one right here, this looks kind of messy. It doesn't look like there's any way where we're going to be able to make those the same, but take a look at this. Remember, this is 2 times 2 times 2. Pair of 2s, so this is going to be 20. The 2 and the x are stuck underneath. And then on this one, again, we've done this several times now, pair of 3s, so this is going to be a 3 on the outside and then a 2x stuck underneath. Whoops, I almost made a sign error here. Remember, that's going to be negative. So if we put the 2 of those together, we get 17 radical 2x. Whoops, make that look like an x. Okay, and then the last one here, look how complicated and ugly this one looks. We've got to see if we can make some like terms here. So let's see if we can reason our way through here. No pairs of 3s, no pairs of x's, but I've got 2y's, so that's a pair. So we're going to write minus 4y, and then what's stuck underneath is the 3x. Let's take a look here. With 27, that's 3 times 3 times 3, so we've got a pair of 3's, so that's going to be a negative 15. We've got a 3 stuck underneath, we've got an x stuck underneath, but again we've got a pair of y's, so we can put that y on the outside, and then we've got 3x stuck here. Now this is where we kind of have to combine our thinking about how like terms work. So notice that we've got the variable y in both of these, and we've got the same root and the same radicand. So what we're really talking about is the variable part of this, the part where we're determining whether or not it's a like term, is the y radical 3x here and the y radical 3x here. This is the part we're talking about to determine like terms. Same base and exponent, same base and exponent, same root right here and here, and same radicand right here and here. So if I have minus 4 of these, minus another 15 of those, then what I have is I have minus 19 of those altogether. Now, we don't do a ton of those problems right now, but it's a good thing to kind of broach this topic, get you thinking about it. I think you have one like this on the assignment. Hopefully this has been a good review. Good luck on the assignment. Go ahead and do the self-assessment and get going. Thanks.